Hello guys, welcome back to my YouTube channel. I'm Naftal. Please remember to subscribe, like, comment and share the video because we are educating ourselves. In today's lecture, we want to talk about electricity and magnetism. So we'll start with magnetism and later we talk about electricity. So we will start with magnetism. And I'm going to define what is magnetism. And I'm going to say is the property of magnets of magnet to attract or repel materials when they are brought to it. This is the property of a magnet to attract or repel materials when they are brought to it. And having that said, we'll talk about what is magnetic fields. We'll talk what are magnetic fields, and we'll start with let's talk about magnetic fields. And because we get magnetic field from a paramagnet or from other types of magnets. Remember, we have a paramagnet, a ring magnet, the host magnet, and the other magnet. So I'm going to use a paramagnet to represent what are fields. This is the north pole and this is the south pole. Remember, a magnet has two poles, the north pole and the south pole. So the north pole is where magnetic fields or magnetic lines originate from and end in the south pole. Those are magnetic fields. Yeah. Now, having that said, we want to see what is the number of magnetic lines a magnet can produce. So let's talk about magnetic flux. We normally use Vi to denote magnetic flux, and I'm going to define magnetic flux as the number of magnetic field lines in space. Assume this magnet has a particular number of magnetic lines it is producing, and that magnetic number is producing is what we are calling magnetic flux. Now, having that said, we want to talk about what is a magnetic flux density. Magnetic flux density density. And we shall define magnetic flux density as, remember we had said magnetic flux to be the number of magnetic field lines in a given space. And our given space we talked about a paramagnet. Now, the magnetic flux density, remember I said we use I to denote magnetic flux, and we use magnetic flux density. We are going to use B to denote that. So I'm going to define them mathematically this way: magnetic flux density to be equal to magnetic flux per unit area. That is the definition of what is magnetic flux density. And from here we can say magnetic flux can be equal to the magnetic flux density times the area. That is what we can see. And we are going to consider now what happens when we have magnetic field lines traveling at an angle into a given area or platform. Consider this. So this is the that where our magnetic fields are going to flow. These are magnetic field density, and we have been told it's going to travel into this material. Now, when we look at this material and the direction and the angle which the magnetic field are traveling into, we can resolve this into the x and y components. So we can resolve this into the x and the y components. So this is the angle which the magnetic field lines are making when we resolve this into the y and the x component. Remember, this is the vertical and this is the horizontal components. Now, when I consider this angle, take this angle to be theta. Now, I'm going to say that y over b will be equal to, remember this is the this is a triangle, and I can say it will be equal to cos theta, because this is the adjacent side and this is the hypotenuse. We will say that the y component or the vertical component will be having fields behaving in this nature. And in the vertical component, we shall say x over b will be equal to sine theta, where we will get x to be equal to b sine theta. Now, that is when magnetic fields are flowing into a given material at an angle. When magnetic fields are flowing into a given material at an angle. So calculating the magnetic flux for each case, that is, let's talk about magnetic flux in the vertical component. So in the vertical component, we said this is the magnetic fields, and we said magnetic flux, we give it as y will be equal to b times area, and our b here is a b cos theta times the area. Now, this means it will be equal to a b cos theta. So if this angle is equal to 0, remember cos 0 is 1, so we will be having our fields as will be equal to a b. That will be the magnetic flux. So the magnetic field density B that we said will be represented as B as the unit of Tesla. So the SI units for magnetic field density is Tesla, and we have this Tesla is equal to other parameters we have in physics. That is, 1 Tesla can be equal to 1 Newton per meter per ampere, or 1 Tesla can be equal to 1 Weber per meter square. Now let's consider a charge moving in a magnetic field. We have a charge that is moving, a charge in a magnetic field. What happens when a charge moves in a magnetic field. And remember, a charge can be an electron, which is negatively charged. Now, if we have that charge that is moving in those magnetic field we have said, consider this is the movement. So we will be having I'm going to draw a bar magnet, and I represent that movement of the magnet that we have said. And these are the ends of the magnet. So this is the north pole and this is the south pole. Now we have the charge at this point and it's moving in this direction. Takes this charge to be Q, and we have, of course, magnetic field lines flowing in this direction. So those are the B fields are flowing in that direction. Now when we look at that charge, it's going to move at a speed, and let's call that speed, it will be moving as V. So V to be the speed of that electron when it is placed in the magnetic fields. Now we will see, remember this is the horizontal side where we have magnetic fields flowing. If I graphically represent that movement, this will be the magnetic fields, and this will be the, of course, the vertical components. Now, and we said that this our charge is moving in a vertical, it is moving vertically up the direction of magnetic field. Now this will be the direction of the charge when it is placed in magnetic fields. Now we will say that this will be the angle that will be this charge will be cutting through the magnetic field as it is moving, and we will say that is, if we resolve it into the x and the y components, we will be having those parameters. Now taking this as the B fields, now this angle, and if we want to find the value from here up to here, it will be a V. Remember, this is like our hypotenuse. If we consider this triangle, that is, if we extract this triangle, this will be the hypotenuse, and this will be the opposite, and this will be the adjacent. Therefore, this side will be equal to B cos theta, and this vertical will be V sin theta. That is, if we extract that triangle, that is what we will be forming. Now the force that will be exerted on the particle will be directly proportional to the force that will be exerted on the particle will be directly proportional. That is, the force that will be exerted on that charged particle will be directly proportional to the velocity of the particle and the magnitude of the charge. But we decided we had formed the vertical and the vertical and the horizontal components. So if we consider the vertical component, where we said that vertical side to be equal to V sin theta, so we will say that force will be directly proportional to we have said the velocity, that is, and the velocity and the vertical component, we said it to be V sin theta times the charge. Remember, the charge is here, and we said force will be directly proportional to force times charge, and the force we said in the vertical component to be V sin theta. Now this means that if I bring this, if I rewrite this one, it will be equal to VQ V sin theta. This can be equal to K QV sine theta. But K is a constant, and K is normally equal to 1. And therefore, if we place 1 here, the force will be equal to QV sine theta. Remember, when we drew that diagram, that is when we drew our diagram to resolve the charge into the vertical and the y component, we decided this will be the velocity of the charge, and this is the angle at which is subtended, and this is the B fields, and we say this will be V cos theta, and this we say it will be V sine theta. Now, if this particle moves in this direction, as in the direction of the magnetic fields, remember these are B fields, so it will not experience a force. It must cut through the fields. So if it moves in the direction of the magnetic field, it will not experience any force. So we will say that the force in the horizontal component will be, which will be, of course, let me say, is equal to 0, because if we bring the factors in there, they will cancel out, because we've said it will not experience any force if it travels in the direction of the magnetic field. Now, having that said, I want to talk about what happens when we have a charge, when a charge is placed, when we have a charge moving into a magnetic field. So consider we have, remember, if I draw this process, as physics we say those are magnetic fields that are moving into the paper. So because we have a blackboard here, we'll say they are moving into the blackboard. The magnetic field are moving into the blackboard, and we have a charge at this particular point, call it charge Q, and it is positively charged. Now, and this will be the, of course, there are so many fields. Now this will be the direction of movement of our charge. The charge will be seen to move as if it is turning around to make a circular path. That will be the direction. Our charge will tend to move in a circular path. And consider this to be the center. And there is a force F that is constraining our charge to move in a circular path. I'm calling that force F. Now, if we use, of course, this movement, the circular movement is derived by you applying the Fleming's. Remember to get the how that particle is moving to form a circular path, we use Fleming's left hand rule, where the curled finger will show us how that particle is going to move, and the thumb is showing the direction of the field, and the fields, because they are moving into the paper. So if we curl our hand this way, we are seeing the particle forming a circular path. Now, that force normally which causes a particle to move in a circular path is called centripetal force. So we have centripetal force, which is constraining our charge to move in a circular path. Now, normally, centripetal force is normally given as M times V squared over R. So in the previous video that I had posted, we had talked about how we came up with this formula, that is centripetal force, how we get all those parameters, and how we bring out this formula. Now, because this charge will experience that force that we had derived earlier, remember we had said force due to magnetic field of a charged particle is normally given as QVB. That is if it is moving in a direction perpendicular to the direction of a magnetic field. But if it is cutting through an angle, we decide it will be QVB sine theta. But if theta is 90 degrees, then it means it is 1. So therefore we will maintain our formula this way. Now this formula will be equal. Now these two forces are equal, which will be equal to so QVB will be equal to MV squared R. Now V can cancel here 1 times and cancel here V times, where we'll be having QP will be equal to MV over R. But remember, the angular velocity of a particle moving in a for circular motion, we have angular velocity or angular frequency, and angular velocity is given as this is omega. We use this symbol omega to represent angular velocity will be equal to V over R. Therefore, we will say that QB will be equal to M omega. That is what we will say. Now, we can find the formula for omega now. That is the angular velocity, therefore will be equal to QB over M. Remember, if we divide it through here by M and here by M, it will cancel out here, and we will bring that parameter of M here. And remember, M is the mass of the electron, and therefore we can find the periodic time and the frequency at which the particle is moving in the circular path. Now, remember we said omega will be equal to QB over M. That is what we have said. Now, remember, omega, that is the angular velocity, is normally given as 2 by f, that is frequency, 2 by times frequency, and therefore we will say 2 by f will be equal to QB over M. Now I divide it through here by 2 by and here by 2 by. So here it will cancel out once, and we remain with the frequency will be equal to QB over 2 by M. That is the frequency of that particle, or a charged particle, when it enters into a magnetic field. Now we will calculate the periodic time. That is the number of oscillations that particle will make in a second. We call it the periodic time. Periodic time, normally represented by T. Now, periodic time is normally equal to 1 over F. That is 1 over frequency, and which is equal to 1. Remember, frequency we said here is QB over 2 by M. That is QB over 2 by M. Now this one, when we resolve it mathematically, it becomes 2 by M over QB. That is the periodic time that particle will take as it makes a particular number of oscillations per second. Now, if we want to calculate the radius of the path, remember we had said charged particle will be moving in a circular path as it enters into a magnetic field. Now, if we calculate the radius for such a path, we will say now the radius of that path will be equal to, remember we said QP will be equal to MV over R. So if I want R, I will just cross multiply here by 1 over QP times 1 over QB times R, then here times R, such that the QP and the QP will cancel out, and the R and the R here will cancel out, and I will form a formula of this kind, and the radius of the path will be equal to MV over QP. That will be the radius for the Let's do one example of what we've been doing. We see whether we are understanding. So here is an example: an electron with kinetic energy over. So we've been told that an electron has a kinetic energy of 10 to power 3 electron volts, moves in perpendicular to the lines of a uniform magnetic field, and the magnetic field we've been told are equal to 10 raised to power negative 4 Tesla. Now, the first question is, we've been given the kinetic energy for such a particle and the magnetic field for such a field. Now, you can calculate it before we do it here, and if you have done, now we will say the first question is compute the periodic time of the orbit. Find the periodic time, calculate for its periodic time, and the periodic time we said is equal to 2 pi m over q b, and m, that is the mass of the electron, we know it, and we know the value for charge. Remember, that is a constant, and we have been given the magnetic field, so it will be 2 by times the mass of the electron is normally 9.11 times 10 raised to power negative 31 kilograms, over the charge is normally 1.602 times 10 raised to power negative 19 times the magnetic field we've been given there is 10 to power 4. That is the periodic time. So, and this will be equal to 3.577 seconds. That is the periodic time. Now we calculate the radius for our particle. Remember, we were given kinetic energy, and we know kinetic energy, that is the second question, is calculate the radius of the orbit. So kinetic energy we know is given by half mv squared, and this will be equal to, now we are calculating the radius, and the radius we say is simply equal to mv over qb. Now we will calculate first of all the velocity for such a particle, and we know the other parameters. So that's why I started with this one. So from here we can say the velocity of that particle will be equal to, if I say that is kinetic energy, remember, was equal to 10 to power 3 electron volts. If I change it into joules, it will be times, remember, 1 electron volt is equal to 1.16 times 10 raised to power negative 19 joules. It will be equal to a half mv squared. Now, if you insert the mass of an electron, and we will get the velocity of such a particle to be 18.7 times 10 raised to power 6 meters per second. And the radius therefore will be equal to, R will be equal to, remember, it is mv over qb, and the mass is 9.11 times 10 raised to power negative 31 times the velocity, which is 18.7 times 10 raised to power 6 over Q, which is 1.6 times 10 raised to power negative 19 times B, which was we were given it as 10 raised to power negative 4, and the radius will be equal to 1.06 meters. This is the radius for our charged particle. It will be making as it moves in an electric field. Now, the next part, I want to say this, that if we have that particle to move into a magnetic field, it will move in an helical. This is what I'm saying. If we have these are the fields, and we have our particle to be at this point, and it's moving into this field, will move in an helical path. That will be the path. That is the path it will describe. Now, let's talk about the force on a current carrying conductor. What will be the force on a current carrying conductor? So we have force on a current carrying conductor. Now, if you consider a conductor of length L, that is, if we have a conductor of length L, so the distance from here up to this end is L, and remember it will be having a cross-section area. This is area A, and it has charges in it. Remember, a conductor has charges in it. Now these charges will be moving at a velocity Vd. That's a drift velocity of the particle will be Vd. Now we are going to say that, remember, we've been calculating how those charges tend to appear or tend to behave when they move into an electric field. Now these charges will move with a drift velocity Vd when this conductor is placed in a magnetic field. So if we have magnetic field pressed this way, so we have magnetic fields, this velocity, these charges will tend to move with a velocity Vd. Now, if we have there are a particular number of charges. Remember, this is one charge, this is the second charge, and there are several other charges that can be able to move. Remember, the positive charges do not move, so it is the negative charges that are moving. So, and we have so many of them in an there are not two as I've drawn this way, because this is an illustration. There are so many when we have an electric conductor. When we have a conductor placed in a magnetic field, so there will be so many of them, and they will be moving with a drift velocity Vd, as we have said. Now, if n is the number of conduction electrons, that's per unit volume. So if n, that is small n, is the number of electrons that can be able to move per unit volume, we will say, so if I take n capital to be the total number of those the conduction charges. Remember, a small n represents one charge, and we've said there are so many in a conductor. So n times the volume. Remember, the volume, that's a cross-section area A and the diameter L, and those will be the total number of charges, and volume is normally equal to area times length, and this will be equal to NaL. Now, having that said, remember we've been calculating the force of a third charge. So the force for our charge when it is in magnetic field will be equal to the total number of charges. Remember the previous we've been doing what is the force on one particular charge. So here we have so many number of charges, and this is the total number of charges, and therefore they will be equal to, force will be equal to this was the formula we said for one particle, but because we have so many of them, it will be Q will be represented as A and L times times VP, and we will say that is the total force that we experienced by all the particles. So if we want to calculate current for one particle, we say is Q over T, but we have that is the current, and the number of charges we said are equal to NaL, and the length, remember length or distance is given by speed times time, so it is the drift velocity of the particles times time, that is Vd times t. Now that is if we want to calculate the current. Now, and the total, remember this represents the charges, and the total number of charges in that particle will be equal to Q times the number of charges, that is the number of charges, and the length we said here will be equal to Vdt, that will be the L, this part is for L, and therefore we will say current will be equal to, we want to calculate for current, so current is given by Q over T, and our Q we said is equal to Q NA VDT over time. So time and time will cancel here, they will say the current L by that conductor will be equal to phase. This will be the current. Now, what is current density? Current density, let's talk about current density. Current density normally represented as J. Current density J is normally equal to the current over area, that is the current per unit area, that is current density. And the current we said is equal to, remember we said it here, is equal to Q NA times the drift velocity, will be equal to Q NA Vd over the area. So these and these will cancel out, and we will get Q N Vd. This is the current density for our charge. Now, we will say, remember we had said force, previously we said force is equal to, that is the total force that we experienced by all of the particles will be equal to N A L Q V D V. Now this part here, Q N V D, that is Q N V D, will be represented by current. So I want to write in that order Q N VD, Q, this is Q and VD. So we have remained with ALB, ALB. The order of this part is current density J, and therefore we will say, force will be equal to J A B L. But remember we said current density is equals to current per unit length. So if I want to get current again, current will be equal to J, that is the current density. Remember, if I want to get current, it will be equal to J times area. So the order of this part is current. Therefore, our force will be equal to IBL. If I rearrange this one, it will become PIL, and this will be the force on a current carrying conductor. So if this current carrying conductor is placed at an angle, it will be BIL sine theta, that is if it is through an angle. Now let's talk about so I'm saying if we have our force, so we have that current carrying conductor passing through, it's placed at an angle in magnetic fields. Because our magnetic field, remember, is making now an angle. We will be having a force equal to IBL sine theta. That will be the force. Now, in vector form, if I write this one in vector form, that is in vector form, remember you can be asked what is the force in vector form. Now this will become, force will be equal to I L, remember it is in vector form, cross B, and that is the cross product. This is the cross product, and I've written it in the vector form. Now we want to talk about torque on a current carrying coil. We want to calculate the torque on a current carrying coil. That is torque on a current carrying coil. Current carrying coil. Consider if we have a rectangular coil of dimensions P and L, so we have our magnetic fields. These are our magnetic fields moving into the paper, and we place now our rectangular coil in these fields. This is the length P and this is the width L. Now if we take this part to represent now the whole coil, that is if we take the breadth, we'll be having something of this nature. So we have our fields moving into the paper. I want to use this one. So we have and these will be our breadth. Of course, there are a number of fields, and this will be our P. Now we are seeing that this coil, it makes an angle theta, it makes an angle as it is. So when placed in a magnetic field, if we apply Fleming's left hand rule, we can determine the direction of the force. The Fleming's left hand rule, this is the Fleming's left hand rule. So if I place my finger this way and the fields were said were moving into the paper, this will be the direction of the force. So this is F1, and the force with torque, that is the turning force, and this will be equal to force 2. Now remember, we've been saying torque. So if I take torque is equal to force times the distance, that is the perpendicular distance, or the moment at V1 will be equal to, that is the force F1, and the perpendicular distance here, if we resolve, will be V cos theta, and for F2 it will be F2 B cos theta. That will be the force and the current carrying on a coil. And remember, we said force is equal to BIL. I want to sort of this one. So having that, we've said force is equal to that is the turning force, or we are calculating the torque, will be equal to force 1 B cos theta. And remember, F1 and F2 are equal, so we can say this to be the force. So if F1 is equal to F2, which is equal to force, and therefore we'll say that will be the force, and the force we decide is to be IBL. So IBL, that is the force, and we bring out this thing. Now this part is area, that is length times the breadth, will be area, it will be IBA cos theta. That will be the new formula. But if that is, we took the breadth of one coil, so if there are a number of coils, then therefore we will say the total torque will be equal to N, that is the total number of, remember this is for one coil, and if we have a several number of coils, it will be N P I cos theta. I can rearrange this one to become N A I P cos theta. Now let's talk about Biot-Savart law. So Biot-Savart law, and this law is well known because it states that if we have magnetic field, that is, if we have magnetic field dB due to current IDL, so if we consider, let me illustrate this one this way, that if we have this is the magnetic field that are moving this way, and we have this is the current carrying conductor, of course this is the B fields, we will say Biot-Savart law states that the current element for such a magnetic field will be equal to these constants. That is equal to this. In the previous video, I had posted how we make this formula, or how we come about this formula. So anybody having any challenge can visit the video. Sin theta over r squared, where you know is the permittivity of free space. So writing Biot-Savart law in vector form, it will be equal to V dB will be equal to mu naught over 4 pi times I. Remember, when we write vector form, it means those factors that will be changing, those factors that only will be changing, times r, that is the unit vector, and r squared. This is showing that this is the unit vector, and the unit vectors in 3 dimensions. Remember, if we take Laplacian or r, represents it is in the 3 dimensions. Now let's talk about Ampere's law. The Ampere's law. Ampere's law. And Ampere's law, it states mathematically that B is equal to mu naught times current over 2 pi A. So if we want to explain this in other words, we can say that the cross integral of magnetic field times the length, that's dl, will be equal to mu naught times the current. So if we work out this one, the cross integral of b dl, that is, remember, if we calculate the cross integral of dl, this means we are calculating the length. And the Power-Savart law states that for a circular, for current in making, of course, you are calculating in a coil, and the meaning it is moving in a circular path, and for that length will be equal to 2 pi times radius, and our radius here is a. So that's why I solve this one into this, and we will say this is Ampere's law, which says that the integral of the product of B, that is the magnetic field, and the dl around a closed loop, this is to show it's a closed integral, that's a closed loop, is equal to current times this constant. So guys, this becomes the end of our lecture today. So in the lecture that will be following this one, we're talking about electricity. So we have talked about magnetism. So in the next lecture we'll talk about electricity, and we'll exclude everything in electricity. So for those who have not subscribed, please remember to subscribe. You can like the video, comment, and share. If you want your other fellow students also to learn, you can share it. Thank you. Goodbye.